So our next section is all about salts, and salts oftentimes get confused for salt in your kitchen. However, salts are more broad than that. So let's define what a salt is in chemistry. It's not just sodium chloride or table salt. A salt is any crystalline substance that is a solid ionic compound. So it's a solid crystalline ionic compound, at least at room temperature. And I'm just going to abbreviate compound here, at room temp, that is made up of cations and anions. All right, you can heat certain salts up to their melting point. However, for most salts, it requires an extreme temperature like 3000 degrees Celsius. So most of these are going to be considered solid, even close to room temperature. Now, it's important to remember that in a crystalline solid, you have this three-dimensional network of cations. And a cation is any atom or polyatomic ion with a positive charge, where an anion is any atom or polyatomic ion with a negative charge. And it's made up of this big kind of brick wall stacking pattern that goes not only in one dimension, but all three dimensions. All right. Now, you might be wondering, why are we talking about this in the acids and bases chapter? Well, acids and bases can react with one another to form water and salt. Specifically, acids and bases will neutralize one another, as we saw in the last video. And when they neutralize one another, they usually form water and salt. I wouldn't say always, but usually they form water and salt. That's why it's so important to remember that salt isn't just NaCl, right? So let's take an example here. All right, let's just take a really easy one. So let's say we've got HCl. This is aqueous combining with sodium hydroxide. Again, this is going to be aqueous, assuming it's already dissolved in water, right? And if we do this, we're going to form water, and water is a liquid. However, the leftover ions will be sodium chloride, and this will be aqueous, but in this case, this is going to be our salt. Okay, and it's important to remember that in this case, the Na plus in sodium chloride, that is going to be the cation from our base. Our base in this example was sodium hydroxide over here. And then our chloride is going to be our anion from our acid. So anytime you mix an acid and a base, it's fair to say the cation is coming from the base and the anion is coming from the acid. All right? And it's interesting. So we can actually collect these products. We can evaporate off the water and we can isolate the salt. So let's just make a note of that. All right, so down here I'll just say these salts can be isolated and dried. And dried, meaning we're going to remove the water. However, there's this really unusual phenomenon, right? There's some salts where when you try to dry them, you can, but only partially. So, however, some salts co-crystallize with water, meaning the water actually gets trapped in the three-dimensional network of the crystal. So they co-crystallize with water in a set ratio. And then when this happens, this is called a hydrate. All right, so it's kind of an unusual example of a salt. But let's show an example that some of you might be familiar with at home. Some of you may occasionally take a bath or soak your feet in Epsom salts, right? You can find these in most drugstores. And Epsom salt is an example of a hydrate. So what it is it's magnesium sulfate as the salt. However, some water molecules are trapped in the crystal structure, and specifically, there are 7 of them. So we show this with a .7 H2O. And what this means is that there are 7 water molecules for every 1 magnesium and 1 sulfate unit. So these are called the waters, or just water, of hydration. It's kind of a unique phenomenon, but these water molecules just pack into the crystal lattice along with the cations and anions. All right, this dot that's in between here, this just means that it's a part of the same crystal structure. So dot equals part of same crystal structure. All right, so this is important to include. If you don't show it as a dot and instead show it as a plus, that implies that they're separate, when in reality they're both combining to form the same crystal. All right, and this is kind of an unusual phenomenon. And some of them, you can actually heat them up to drive off the water. So let's just put a note here that some hydrates, not all of them, but some hydrates, can be heated to a point where they lose some or all of their waters of hydration. So for example, if you were to take Epsom salts and put a sample of Epsom salt into a blast furnace and heat it up to, let's say, 2000 degrees Fahrenheit, you could leave it in there for a few minutes, and then when you come out, you'd be left with only magnesium sulfate, because the temperature would be high enough for those water molecules to essentially vibrate their way out of the crystal lattice and evaporate. But it requires usually pretty high temperatures to remove all of them. At moderate temperatures, you might lose some of them, so maybe the 7 goes down to a 3, but it requires pretty high temperatures to remove them all. All right, and it's hard to tell right away which ones allow you to lose all of them, which ones form hydrates. I'm not going to test you on any of that. I just wanted to show it to you because it's kind of this unusual phenomenon with some salts. All right, that leads me to my next point, where often in hospital settings, you are told to add an equivalent of salt. And to be honest, this was a term I had never heard of after getting my PhD in chemistry. It's something that never came up in my field, but it is something that occasionally pops up in the healthcare field, so I did want to present it. But it is the amount of salt that will produce 1 mole of positive charges. A positive charge when dissolved or dissociated. All right, so maybe in a hospital setting, you have to, put in a saline bag into a patient. You might need to measure out the various salts that go into that saline bag, and it might be measured in equivalents, which is what we're discussing here. So let's take an example. And it is a little bit confusing, but bear with me on this. So in this example, we want to determine the numbers of equivalents of salt in 0.050 moles CaCl2. So let's kind of break this apart. So if we take CaCl2 and we break it into complete ions, we would be left with a calcium 2 plus cation, plus we would be left with 2 chloride anions, right? But the key term here is this only looks at the positive charge. So if we look at, well, the positive charge here, this calcium is really the only thing that we care about in this problem, okay? So if we think about this, 1 mole of Ca2 plus has 2 moles of positive charge. Another way of writing this is it has 2 equivalents. So let's just say i.e. 2 equivalents. All right, so that now we can kind of work through this problem a bit more clearly now that we've broken it down. So down here we could say, well, we've got 0.050 moles of CaCl2, and for every mole of CaCl2, we get 1 mole of calcium 2 plus ions out, right? Because that's what we're seeing on the other side of the equilibrium. All right, so now we've canceled out our moles of calcium chloride. We got moles of calcium 2 plus, but that's not what we want. We want to find moles of our positive charge. So I'm going to say for every 1 mole of calcium 2 plus, we get 2 equivalents of our positive charge, right? So now we can cancel out this, and it's important to remember that this is equivalence of positive. All right, and now if we go through and we do the math for all of this, it should be pretty straightforward. We get 0.10 equivalents of our salt. Okay, and furthermore, if you're in a hospital setting, occasionally what they do is they say milliequivalents. So how many milliequivalents, MEQ, are in 0.10 equivalents of CaCl2? Well, this is just basic unit conversion at this point, right? So don't overthink this. If you remember, 1 milli anything, milli is just code for 10 to the negative 3, right? So 1 milli equivalent is the same thing as 10 to the negative 3 equivalents. These are synonymous, right? So now we can turn this into a unit conversion problem. We can say, well, 0.10 equivalents of CaCl2 times 10 to the negative 3 equivalents for every 1 milli equivalent. Well, if we work this out, we're going to get an answer that's 1.0 times 10 to the second milli equivalents of salt. So this would be the final answer for that. All right, I hope that helps, but feel free to email me if you have any questions. There's also a number of really good practice problems in the book, so I would recommend that you try working on some of those in your spare time.